are going to explain about the project title Darknet Traffic Analysis, Investigating the Impact of Modified Tor Traffic on Onion Service Traffic Classification. Introduction. The project's primary objective is to improve network security by accurately categorizing network traffic into two distinct categories, Tor services and Onion services. Tor is a privacy network enabling anonymous internet use. Its traffic encompasses various online activities with enhanced privacy measures. Onion services are websites or services on the Tor network designed for anonymity, making it hard to trace the traffic source or destination. This classification is essential for detecting and mitigating potential security threats within computer networks. The project employs passive network analysis techniques in combination with machine learning classifiers to assess the feasibility of classifying Onion service traffic. This involves the monitoring and analysis of network traffic without actively participating in network activities. The ability to distinguish Onion service traffic from other types is crucial for several security-related purposes. This includes identifying and combating illegal websites operating within the Darknet, shutting down command and control servers for botnets, and controlling access to sensitive systems to prevent unauthorized entry. To enhance the accuracy of the classification process, the project takes several steps to modify and enrich datasets. This includes working with existing datasets like Tor, no-defense, and creating a modified dataset known as WTF-PAD. Additionally, the project considers the OS dataset, which contains information about Onion services. These modifications are made to improve the precision of traffic classification. Objective. The project's primary aim is to develop a system that can accurately differentiate between Onion service traffic and other types of traffic within the Tor network. It investigates how modifications made to Tor traffic impact the accuracy of this classification. This is crucial for identifying and addressing potentially malicious or illegal activities in the network. Another objective of the project is to pinpoint the most significant combinations of features, attributes or characteristics within the dataset that play a key role in classifying traffic. By identifying these influential features, the project aims to understand what factors are most important in achieving accurate classification results. In addition to the technical aspects of classification, the project also delves into the background and context of the Tor network and Onion services. It reviews existing literature and related work on Tor traffic classification. This step helps the project build upon prior research and gain a comprehensive understanding of the field. The ultimate goal of the project is to contribute to both network security and user anonymity. By effectively identifying and classifying traffic within the Tor network, particularly Onion services, the project aims to enhance security measures and address potential security threats. This contributes to the broader objective of ensuring a safer and more private online environment for users. Software and hardware requirements of the project are: hardware requirements are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language used in the project is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing the necessary Python libraries and packages that will be used throughout the project. These libraries typically include data manipulation, that is pandas, machine learning, sklearn, and data visualization, matplotlib tools. Exploring the dataset. This phase involves getting familiar with the project's dataset. Two main datasets are mentioned: WTF-PAD dataset and no-defense dataset. WPF-PAD dataset. This dataset is a modified version of the Tor network traffic data. It appears to be adapted or padded in some way to investigate the impact of these modifications on the classification of Tor and Onion services. No defense dataset. This dataset likely represents the original Tor network traffic data without any additional defense mechanism or modifications. It serves as a reference or baseline for comparing the performance of the classification algorithms when applied to the modified dataset WTF-PAD. Exploring the datasets typically includes loading the data, examining its structure, and understanding its features, and gaining insights into the data's content. Feature selection. Feature selection is a critical step where the project identifies and selects relevant attributes, features from the dataset that will be used in the classification process. It helps in reducing the dimensionality of the data and improving the efficiency of the machine learning model. Data pre-processing. Data pre-processing involves tasks such as handling missing values, scaling features, and converting categorical data into a suitable format for machine learning algorithms. It ensures that the dataset is in a clean and usable state. Splitting the dataset into train and test. To evaluate the performance of machine learning models, the dataset is typically divided into two subsets, a training set and a testing set. The training set is used to train the model, while the testing set is used to assess how well the model generalizes to new unseen data. Building the model. In this module, the project constructs the machine learning model. It involves selecting an appropriate algorithm and configuring it for the classification task. The model is designed to learn patterns and relationships within the data. Training the model. Once the model is built, it is trained using the training dataset. During training, the model learns from the provided data and adjusts its internal parameters to make accurate predictions. This is a critical step in preparing the model for actual classification tasks. Flash framework with SQLite for sign-up and sign-in. In this module, the project incorporates the Flash web framework along with an SQLite database to implement a user authentication system. Users can sign up and sign in, allowing them to access and interact with the project's functionality. The given input is pre-processed. This module involves preparing and cleaning the input data. Data pre-processing tasks might include handling missing values, feature selection, and any other necessary data transformations to ensure that the input data is in a suitable format for the machine learning model. The trained model is used for predicting the result. The project utilizes a trained machine learning model to make predictions based on the pre-processed input data. The model has previously been trained on a dataset, and now it's used to classify or make predictions on the provided data. Final outcome is displayed. Once the predictions are made, the project displays the results to the user. The final outcome may include information about whether the input data corresponds to Tor services or Onion services based on the trained model's predictions. In the extension phase of the project, an Ensemble model is introduced. Ensemble models combine the predictions of multiple base models to improve overall accuracy and robustness. In this project, the Ensemble model aims to enhance the classification results, making them more reliable. The project's front end is developed using the Flash web framework. This interface allows users to interact with the project, input data, and view results. Additionally, user authentication is implemented to ensure that only authorized individuals can. Algorithms used in the project are KNN, K nearest neighbor. KNN is a classification algorithm that works by finding the K nearest data points to a given point based on chosen distance metric. In the project, KNN is used to classify network traffic into Tor services or Onion services by looking at the class labels of the K nearest neighbors of a data point and assigning the most common class label to that point. Random forest. Random forest is an ensemble learning algorithm that combines multiple decision trees to improve classification accuracy. In the project, Random Forest creates a collection of decision trees, each trained on different subsets of data and features. These trees vote on the classification, and the final prediction is determined by majority vote enhancing the reliability of classifying network traffic. SVM, Support Vector Machine. SVM is a classification algorithm that finds the best hyperplane to separate data points into different classes while maximizing the margin between them. SVM is used in the project to create a clear boundary between DOS services and onion services by learning the patterns and characteristics that differentiate them in the network traffic data. Comparison graph. Models are compared with the parameters accuracy, precision, recall, FN score. This is the accuracy comparison graph. On the x-axis we have the accuracy score and on the y-axis we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is precision comparison graph. On the x-axis we have the precision score and on the y-axis we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is recall comparison graph. On the x-axis we have recall score and on the y-axis we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is FN comparison graph. On the x-axis we have FN score and on the y-axis we have the algorithm name. The FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the dataset folder. To implement this project, we have utilized the WTF-PAD dataset. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook file. This Jupyter notebook file contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we will copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flash framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up link. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created, and then click on sign in button. We have logged in successfully. So here we need to enter all these parameters to predict network traffic into two categories: Tor services, general Tor traffic, and onion services, traffic related to hidden services within the Tor network. So I'm entering the parameters F1 -1, F2 -1, F3 -1, F4 -1, F5 -1, and F6 is 1. After entering all these parameters, click on predict. So here we got the result as OS, which is onion services. Onion service represents the traffic associated with Tor's hidden services, providing anonymity for both the server and the user. The project aims to identify and classify traffic related to onion services. Now we will enter another set of parameters. I am entering the parameters. So here I have entered all these parameters. Now click on predict. So here we got the result as WTF-PAD. WTF-PAD refers to a modified dataset used in the project. It's created to evaluate the impact of modified Tor traffic on the classification of onion service traffic. This dataset helps assess the effectiveness of the classification algorithms when the Tor traffic has been altered or padded. The goal is to predict whether the given network traffic is related to onion services or falls under the modified Tor traffic category WTF-PAD. The selected features F1 to F6 play a crucial role in making these predictions. Now click on sign out. The conclusion of the project is: the project effectively assesses how modifications made to Tor traffic data affect the classification of onion service traffic. It discovers that the accuracy of classification can be influenced by these modifications, shedding light on the importance of considering the integrity of the data in the classification process. The project identifies the feature combinations within the dataset that have the most significant impact on the classification task. These influential features are assessed for their contribution to the accuracy of classifying network traffic as either Tor or onion services. The project delves into the performance of various features and their influence on the classifiers. It provides valuable insights into how different features impact the performance of the classification algorithms, offering a deeper understanding of how to achieve accurate results with different sets of attributes. The project emphasizes the critical role of traffic analysis and machine learning techniques in effectively classifying and comprehending the behavior of onion service traffic within the Tor network. It underscores the significance of these methods in enhancing network security and detecting potential security threats.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.